so we're continuing in our this coverage of refrigeration and heat pump systems. Today we'll spend a lot of time on practical vapor compression refrigeration, especially split systems, which you find in your home. So you have something on the outside, a box on the outside of your home, a box on the inside of your home that's split by some distance, and the condensing units outside and the evaporator and expansion valve are in the inside. We'll talk about the line set, evaporator, capillary tubes, TXV, some other things. And then we'll talk about multi-stage or cascade refrigeration systems, and then talk about the practical aspects of selecting refrigerants and the changing environmental regulations associated with refrigerants. So here is what's on the outside of your house. In a split system, you have the compressor, and it's surrounded by the condensing coil, the heat exchanger. The air is drawn, outdoor air is drawn across that heat exchanger, the condensing coil, and a fan then propels it up and out. And that's the condensing unit or the condenser unit. It's the condensing unit is the combination of the compressor and the condenser. Then you have coolant lines or line set. They're copper lines. They're typically flexible and they have to be bent and contorted based on making it weave from the inside to the outside. The people that install it make it work. Sometimes they're straight run and then what are they, brazed together? Not soldered, but brazed together. But then they have to get up here to where they have an expansion valve and then the evaporator coil. And so you have an air handler. It draws air in. Maybe you have it ducted or you just have a grill. You have to then filter it. Don't forget the filter. Clean your filter, change your filter, always, often. They're very cheap in comparison to a repair bill. And then blow that air across the evaporator coil. It cools it down. You'll have to have a drain pan for some draining off some liquid, because often our homes are hot and humid, and when you cool it down, it dehumidifies the air. That water comes out, has to be drained out, often just drips to the outside of the house somewhere in a safe spot. So what we haven't covered before, the refrigerant lines. One is a suction line and one is a liquid line. One takes refrigerant from the outside into the house, and the other from the inside to the outside. They make the loop. And so what's happening, how do they get this name suction line? Well, when the compressor kicks on, the system is at an equilibrium, and everywhere it's the same pressure before it kicks on. And when it kicks on, the compressor starts drawing in on one line and discharging at a higher pressure the other line. And so they say the compressor starts sucking on the line. So it's a suction line. That's what's happening. So the suction line is what's feeding the compressor. So the suction line goes to the compressor and the refrigerant is leaving the evaporator and being drawn toward the compressor. All right, what about the liquid line? Well, that must be going into the home. So what comes out of the condenser? Out of the condenser is liquid. And so the liquid then goes in the liquid line into the home. And then when it gets to the expansion valve, it expands, drops pressure, and then it evaporates or boils in the evaporator. It provides that cooling. Make sense? Suction line, liquid line. So in this illustration, you had the major components. You had the compressor, condenser, expansion valve, and evaporator. For practical introduction to the residential split system air conditioning system we just talked about, I have a clicker question for you. Here's a clicker question. Where is the suction line? Is the suction line between the compressor to the condenser? Is that the suction line? Or is it condenser to evaporator or expansion valve, etc.? So I'll let you read that question and answer it. I just clicked it on, and you have right at 25 seconds. So where is the suction line? All right, so everybody's in. Well, we just mentioned it, did I not, on the previous slide? And how does it get the name suction line? It's what the compressor's doing to it. It's drawing fluid, pulling it out of that line and discharging it. The compressor's discharging it to the condenser. So when you turn it, when the system is off, its pressure is equal everywhere. But when the system starts to run, you have a high pressure side and a low pressure side. And the compressor is what draws out the refrigerant out of the low pressure side to make it low pressure and discharge it. If it wasn't for the compressor, you wouldn't have a delta P, right? So where is the suction line? Right there. So what is that? From the evaporator to the compressor. So we got almost everybody. How about this question right here? The next question, where is the liquid line? Well, it's good to recall that two things are close together on the outside of the house. It's the condensing unit that's on the outside of the house. What are the two things that are close together in the condensing unit on the outside of the house? And so these two things are close together on the outside of the house. Well, the other two things are close together on the inside of the house, aren't they? And as soon as it expands, it's now cold. It's cold right at 4. And it's ready. So you don't want it to be cold for a long distance. You want it to get cold and start cooling and go right away. These are close together on the inside. These are close on the inside. These are close together on the outside. And so this right here is the, let me see if I can clean this up a little bit. This right here is the liquid line. It goes from the condenser all the way up to the expansion valve, which immediately follows to the evaporator. So which answer is that? From the condenser to the expansion valve. So this down here is the suction line. What's the pressure in the suction line, high or low? The pressure in the suction line is low. What's the pressure in the liquid line, high or low? It's high. It's high. High pressure in that liquid line. So the refrigerant flows from the outside to the inside of the house in what line? Easy question. Ooh, what happened here? Why do we have confusion on that one? I thought this would be 100%. It flows from the outside to the inside. All right? What's on the outside? It goes to the compressor, then the condenser. It's at high pressure. It's now ready to go back and start to hit that expansion valve and then evaporate. What goes between the condenser and the expansion valve? The liquid line. I don't know why we have 7 wrong. Okay. Now this is a tougher question, but which line is hot? There's 2 lines, and typically you can go on the outside of your house and you'll see the 2 lines. And you can actually put your finger down and touch one of the lines, and then put your finger down and touch the other line, or put your hand on it and grab the other line. Okay? Which one of these lines is hot? The suction line is hot, the liquid line is hot, or they both have the same temperature. They're neither hot nor cold. Which line is hot? Well, this is more challenging because you have to say, what is the state of the fluid that came out of the evaporator? So think about the evaporator right here. And the fluid comes out and it goes to the compressor. And from the compressor it goes over. This fluid right here at this state, Is it high pressure or low pressure? Low pressure. And it just evaporated at low pressure. What about the temperature of that fluid coming out of the evaporator? Hot or cold? Well, is it saturated vapor? Is it saturated vapor? Is the temperature of the saturated vapor equal to the saturation temperature at that pressure? Is T equal to T sat at whatever pressure it is? Yeah, it is. Let's go out here. Let's do this one. What about the pressure after the compressor? Is the pressure high? True. And then it goes through the condenser. Tell me a little bit about the pressure coming out of the condenser. High pressure. High pressure. Okay. Is it saturated liquid coming out of the condenser? It's saturated liquid, just like it was saturated vapor out of the evaporator, saturated liquid out of the condenser. True? Is the temperature at which it comes out of the condenser, is that equal to the saturation temperature at the pressure of the condenser, which is high? If you got that straight, then you can just say to yourself, is the saturation temperature high, hot or low, cold, but depending on the pressure, isn't it? And so in general, if I have a diagram, let's say, what is it? Pressure temperature diagram, and I have a slope of a line like this, which is the saturation pressure as a function of temperature. And I can think about, if you give me a pressure, I can read off a temperature, the saturation temperature. Or if you give me a temperature, I can read off the saturation pressure, either way. But what we have here is if you have a lower pressure, what do you have? A lower temperature. If you have a higher pressure, you have a higher saturation temperature. That's a lot to absorb. You know, chapter 3 of this textbook is such a fundamental chapter. It's all about fluid properties, and yet it's so easy to forget the basics. So armed with that, which line is hotter? Which line is hot? That's an oxymoron when you first think of it. You think vapors are high temperature because your experience is I have to heat something up to make it boil, vaporize. That's your intuition, that's your experience. Vapors are higher temperature than liquids at the same pressure. But you're comparing a liquid at high pressure and a vapor at low pressure. And here, the vapor's cold and the liquid's hot because of the pressures. Okay, so let's see how you did. Yeah, that's a harder question, isn't it? Isn't it a harder question? So there we go. How do you like these questions? All right, this is a very challenging question. Which line is insulated? The suction line is insulated, the liquid line is insulated, or neither of the lines are insulated, or both of the lines are insulated. Insulated. Why do you insulate? To prevent heat transfer. What are you going to insulate to prevent the heat transfer to? Well, between the inside of the house and the outside of the house is probably mostly just ambient temperature. So you're going to insulate to prevent heat transfer with the ambient environmental temperature. Okay? That's what you're going to insulate to if you insulate the lines. So now, which lines are insulated? The suction line? I forgot, is that hot or cold? Cold. The liquid line? Is that hot or cold? I forgot. Yeah, right. Neither line, let heat transfer occur with the environment, I don't care, or insulate both of them. Right? Insulate both. So those are your options. Let's go ahead and let you answer that. Well, that was a very tough question, okay? I don't know exactly how you did. Should I just pull them up and then talk about it, or talk about it then pull them up? Pull it up to see how your class did. All right. Well, I think the people who went for D were thinking, when in doubt, just insulate everything. I honestly think that's probably the case. Just when in doubt, insulate everything. And that's usually it's not the preferred approach. And let me do this. One of the lines that comes out is hot. Which line comes out is hot? Liquid line. If you touch it and it's running, you can do this without getting electrocuted. Don't go touching electric wires, but you can find your condensing unit. You can find that liquid line. And you can put your hand down there in the middle of August, running hot. You know it's running because you need to keep your apartment cold or you need to keep your house cold. You could touch that line. You'll find out, guess what? It's hot. It's really hot. You're not going to keep your finger on it very long if it's running properly. Okay? If it's a sick unit, you need to have a service technician come out. That's one of the keys. It's not running very good. Okay? But you won't be able to hold on to that line. It's so hot. Okay? Now, if you have additional heat loss from that liquid, it's only going to be cooler right before it sprays across the expansion valve and starts cooling. It's going to be best for performance. It's only going to help it a little bit. Dump the heat to the environment if you can. So the hot line's never insulated. How about the cold line? If you put your finger down on it, it's cold because it was just cooling the air. The air that you want to cool down to 55, maybe you have the refrigerant at 40 or 35 or something like that. Maybe not that cold, 38 or so. Inside the evaporator, it's cold, it's chilly, like the inside of your refrigerator. Now, that is done evaporate. It's now all vapor. It's getting back to the compressor. Would it be good to ingest cool vapor into the compressor or warm vapor into the compressor? Cool vapor into the compressor is always better. More dense, the less work per unit mass that the compressor has to do. And actually the compressors get very, very hot because what comes outside of the compressor, it's all beat up and it's spanking hot. That's the hottest. If you could ever get your hand in there, you wouldn't want to, and feel the discharge from the compressor going to the condensing coil, it would be very hot. Very, very hot. So that refrigerant, the cooler you can bring it in, vapor in, great. If it's warmer, it'll still do its job. It'll be harder on the compressor to do its job. So which line do you think they insulate? The suction line. They don't want any additional heat going to the suction line. Keep it cool. All you're going to be doing is superheating it. It came out saturated vapor out of that evaporator. You don't want superheated vapor going into the compressor. Try to keep it saturated vapor. When it gets up to this evaporator, and often they're shaped like an A, they call it an A coil, and we talked about this before. So the refrigerant comes in, and there's some metering device, some expansion valve, something to drop the pressure. Here, this is really not dropping the pressure, but it's putting it into, splitting it up and putting it into, I can tell there's going to be 3 on this side, 1, 2, 3, and 3 on this side, 1, 2, 3. So it'll have 6 paths through the evaporator that the refrigerant can go in. And then it'll be collected out here, 1, 2, 3, 1, 2, 3, collected into a manifold in the suction line and returned, right? So the liquid line comes in, it's split into 6 little lines. But what's interesting right here is they have the coiled up lines. It's like, why do they coil it up? Why didn't they just take it there and push it over here? Well, that's a capillary tube. It's just a tube of a specified length that when it's up and running at the right pressures, it'll have the right pressure drop for the flow rate through it. And so they're highly engineered, they're very cheap, but once they've been benchmarked and the performance is known, then the engineers over many, many years, many devices have said, this many inches of that diameter capillary tube will give you the right pressure drop for the flow rate you want. And they're super cheap once you build them. It's just, that's it. That's my metering device. That's my expansion valve. That's the cheapest metering device, the cheapest expansion valve that you could implement. And they're still around. If you take a look at your refrigerator, probably pull it off and maybe dust it off a little bit in the back. Clean the coils a little bit. You'll probably see a capillary tube, just a small line that's wound up. Okay. So it is a throttling device. It's almost, the first time you see it, almost too good to believe. Here is something, 8 bar, 45 degrees C. What is the pressure? High. What is the temperature? High. Coming out, 0.6 bar. Okay, it had a pressure drop because it went through a small little orifice, not an orifice, but it's a capillary tube, a small diameter tube. What's the temperature? That's the remarkable thing. Hold it. It went in 45. There's no heat transfer. Nope, none. It's adiabatic. And yet it comes out -20. Impossible. No, it's not impossible. This is what you're studying. This is it. This is thermodynamics. This is real life. This is what makes you happy in your car and automobile and house and your air conditioning and all your beverages and foods that you have in refrigerators. So again, this is that hard to understand, but it's because this is dropping the pressure. It wants to go out into the vapor phase. Some of it will evaporate. It'll flash. Most of it will still remain liquid. The mixture will drop temperature because it takes a lot of energy to break those bonds between the liquid molecules to get some of them to go into vapor phase. Were those, what type of bonds? Something molecular bonds? Intermolecular bonds. How they attach and are held, feel the effects of each other in the liquid phase. Well, not always do we have a capillary tube. Sometimes you have a device like this. It's called a TXV, thermostatic expansion valve. And that's a little more highly engineered, and it'll actually have a sensing unit on it. This bulb comes down, and it senses the temperature coming out on the suction line. And then it'll say, okay, you're coming out a little too warm. More refrigerant goes in. Okay, the sensing element's a little too cold. It'll cut off the refrigerant and won't feed it as much. Here it is right here. Off the top, there's a little line. It's squiggly. It's going over here. Right there's the bulb, and it's usually wrapped in something to keep good contact with the suction line. So this is the suction line. Can you tell a difference in the diameter? That's the suction line. This is the liquid line coming in. Which one is larger diameter? Why? Why is the suction line? Do they have the same mass flow rate through the lines? The same mass flow rate. But the density or the specific volume is much different. The liquid is more dense, right? So it has a higher, the density of the liquid is more dense, so the density of the liquid is, much greater than the density of the vapor. So you need more room for that suction line. You need a larger diameter for that suction line for the same mass flow rate. The speed may not be the same, the velocity may not be the same in them, but you don't want a thermatically higher velocity in the liquid versus the suction line. One thing we don't talk about in this class, but it's the lubrication. It's the oil. There's oils in these units. And you need the oil to lubricate, especially down in the compressor. But the compressor discharges fluid out the compressor. The refrigerant goes out, but a little bit of that oil goes out. And engineers have to worry about getting that oil back to the compressor. Okay? And we don't talk about it in this class, but one of the ways is don't make the lines so big that there's not enough sweeping velocity to sort of carry that liquid along, that oil along with it going back. Also, there's little traps and ways to not let it get stuck over there and kind of sweep it up and pitch it over. You can run into big problems if you turn on the compressor. It starts with all the oil in it, and then all of a sudden the oil's somewhere else in the system and it can't get back to the compressor. But so anyway, this is a TXV. It's fed by the liquid line. The pressure drops across it. The distributor just helps get it out. There's no capillary tube in it. All right. Here's a good maybe picture of it. You have the bulb for sensing it. When they buy it, that's coiled up. The technician can stretch it, put it where he wants it, tape it to, or strap it to the suction line. The smaller inlet, the larger outlet. This one would just feed one evaporator. It wouldn't go to a distributor and then spread it out. We talked a little bit about commercial. Sometimes you'll see that terminology, split systems for residential. You'll see packaged rooftop units for commercial. So if you get up onto the roof of a building, or maybe you look down out of an airplane and you see a roof of a building, you often see many, many packaged units in a line, easy to service. If one goes offline, the others will still keep the building pretty comfortable. All right? You crane them in, crane them out. They're big and heavy. What's inside? Well, just remember a couple things. You take return air from the building up through the roof, and you throw back out nice cold air to the building. And it could be ducted for the distribution inside the building, but even if it's so cheap, they just dump it back into the building. But often it's ducted. The air comes up, it goes through a filter, it then goes through coils. These are cooling coils. That's going to be my either condenser or evaporator, I forgot. Is this cooling coil the evaporator or the condenser? It's your evaporator. We're talking about summer air conditioning applications. It's now cool and it's blown back down into the building through the blower. Okay. If you have a outdoor air, you can bring in some, and you can have mechanical ventilation, meaning that there is some outdoor air, and then you have to expel some of the return air so that you have some. In the trade, they prefer not to use the term fresh air or clean air. It's just outdoor air. It may not be it may not be super healthy to breathe it in a city, so they don't say clean air. They just say outdoor air. It's whatever you've got downtown Beijing, right? You ever been to Beijing? They say the air is terrible. I've never been there. People sometimes wear masks. They can't see buildings sometimes in the cloud of the pollution. So it's just outdoor air, okay? So they bring in outdoor air, outside air, and you get mechanical ventilation. Way over here you have another set of coils, and then you have air from the outside pass over those coils and cool the refrigerant. That's your condensing coil, all packaged together in one unit. Refrigerant doesn't have to be piped anywhere. It's all right there, assembled in the factory. You just hook up the electricity and away you go. And have the ductwork. And you'll have your compressors right here running, and a little line set going across to the evaporator and then back and forth. Okay. So I have seen a few packaged rooftop units in homes, but they're in the Dominion. Those homes are like mini malls, 10,000 square foot or something. You know, it's not the home that I'm ever going to live in. But yeah, if you have a huge home and you make millions of dollars a year, you may have on the roof of your home a packaged unit for air conditioning. And you may have it just for your private gymnasium, right? Private basketball court or something. Okay, let's set up and solve a problem. So refrigerant 134A is a working fluid in the vapor compression refrigeration cycle. It has two evaporators. Here's evaporator 1 and evaporator 2. It has one condenser. Okay. The saturated liquid exits the condenser at 36. So it's sat liquid at 36 degrees C. The refrigerant in the evaporators are at -4 and -26. Well, this one's probably the -4, and this is the -26 degrees C. Saturated vapor exits each evaporator. So this is right here at 7, saturated vapor, and at 6, saturated vapor. Now, why do I say it's -4 for evaporator 1? Because what is this? Expansion valve. What about the pressure at 4 versus the pressure at 5? Which pressure is higher, 4 or 5? 4 is higher pressure, so 5 is going to be lower pressure. It's going to be lower temperature for that evaporator. The first evaporator has a refrigeration capacity of 1.3 tons. So this Q dot is 1.3 tons, or ton, just put ton without the plural. And the second Q dot is 0.9 ton. Well, that was the 211 kilowatts per, what is that, kilowatts? Rate of refrigeration, yeah, 211. Determine the mass flow rate of the refrigerant through each evaporator in kilojoules per second. So we want to find m dot 1 and m dot 2. And then the net power input to the cycle, and so W dot, it only comes into the compressor, so it's W dot C. There's no other input of work or power into the cycle. That's what makes it run. We have no fan powers. In the real world, yes, there's fan powers, and you need to account for them, and engineers need to try to minimize the power consumption to run the fans to blow the air. But there you go. So how am I going to solve for m dot 1 and m dot 2? We have an energy balance around the first evaporator. Q dot 1, let me put a 1 on there and a 2 on there. Q dot 1 is equal to the mass flow rate through the first evaporator times the enthalpy at 4 minus the enthalpy at 7. Oops. Enthalpy at 7 minus enthalpy at 4. Okay, well, what is the enthalpy at 4 and 7? Well, before we get too far into it, make a table and organize your results. Because you can see that to solve for this mass flow rate, I'm going to have the enthalpies. The same thing for Q dot 2 is equal to m dot 2. To solve for m dot 2, I'm going to need to know the enthalpy at 6 minus the enthalpy at 5. I need to know the enthalpies. And what about the power to run the compressor? It's going to be the mass flow rate 1 plus mass flow rate 2. Isn't that the total mass flow rate through the compressor? Times that enthalpy 2 minus enthalpy 1. And it's probably a few steps to get each of these enthalpies. So make a table and then fill it up. So states. How many states do I have? 1, 2. Now, if I had an efficiency for the compressor, I'd think about 2S and 2 actual. But nothing about an efficiency of the compressor. I'll assume it's isentropic, so I just have 1 state 2. Okay, and then 3, 4, 5, 6, 7, 8. Are there any other states that need to be considered? And then think about getting the pressure, maybe in units of kilopascal, temperature, maybe degrees C, maybe quality, maybe enthalpy, maybe entropy. Those are kind of the standard properties that help us solve these problems. And I like to just walk through the pressures, okay, and walk through the temperatures as best as possible. So the pressure at 2 is equal to pressure at 3, isn't it? It's the high pressure, and it's the saturation pressure for 36 degrees C. And so T3 is equal to T2. So I find the saturation pressure at 36 degrees C. That is, this is Psat, this is P2. Okay, does that make sense? So does anybody have a table or appendix? Do you want to try and follow some of these numbers, or you just want me to give you the high-level outline? Yes, sir.
I have one question. Can we use like Cp times T7 and Cp times like delta T?
No, because it's changing phase, and you want to avoid using specific heat in the two-phase region. The specific heat really is undefined in the two-phase region. Yeah. Is T3 equal to T2? No. Yeah, what I need to do is I need to do it this way then. Do the Psat, that's what I should do, thank you. The saturation pressure at 36 degrees C, which is state 3, that tells me the highest pressure, the pressure of the condenser, and now that's P2 is equal to P3, right? Go backwards, right? So what is the saturation pressure? Let's just do 911. 911, okay? So it's 911. Now, we know that this temperature coming out at 2 is much higher than 36. So it's going to be superheated vapor at that 911 pressure, and then it's going to cool, then it's going to hit the saturation state, then it's condensed, and it comes out saturated liquid out of the condenser. At this point, you can get the enthalpy of the saturated liquid. The enthalpy is like 102.3. And you can also get the entropy if you want to. You don't really need it at state 3. Now, I go through the expansion valve. What about the enthalpy at state 4? Isenthalpic. That's an expansion valve. It's isenthalpic. Okay. What about the pressure at 4? Well, the pressure at 4 is equal to the saturation pressure at negative 4. So state 7 had a negative 4. So you get Psat at negative 4, which is 253 kilopascal. And that pressure is the same pressure as 4, 253 kilopascal. All right. Now, when it goes into state 4, it flashes. And you can actually calculate the quality at state 4. The quality at state 4 is 0.277. 28% does something. 28% is already in the vapor state, leaving, 72% liquid. Does that make sense? It goes across this expansion valve. The quality at 4 is 28%, 20.277. Okay. So now that gives us the enthalpy at state 7 is just from saturated vapor at state 7. And you can look up that one. This is 248.9. So we got the enthalpy at 7, the enthalpy at 4, the Q dot. So we can calculate m dot 1 right away. We've worked enough of the table to get m dot 1. And so maybe I'll just tuck it over here. M dot 1 is equal to 0.03136 kilograms per second. Let's continue on through the table. What about enthalpy at 5? Well, the enthalpy at 5 is the same as enthalpy at 4 because it goes through an expansion valve. So enthalpy at 5 is 102.3. I think I have these lines a little too close together, don't I? All right. Yes?
How do you find the quality at step 4?
Okay. The quality at 4 is based on the enthalpy at 4 and the enthalpy of saturated liquid and the enthalpy of saturated vapor at 4. And those values, H of F and H of G, depend on the pressure or the saturation line of negative 4 degrees C. That pressure at 4 is 253 kilopascal. All right. Okay. Let's continue on. So the enthalpy at 5, and then you can get the quality at 5, just like you get the quality at 4. And the quality at 5 is 0.390. 39% is now in the vapor state. More is in the vapor state because it's not just negative 4 degrees C, it's negative 26 degrees C. It's a lot colder. Okay. And I should have put that number here. It's negative 26 degrees C. This is negative 4 degrees C. All right. So that's the enthalpy. Now what about 6? What is the pressure at 6? Oh, I forgot to say what's the pressure at 5. The pressure at 5 is the saturation pressure at that negative 26, which is about 102 kilopascal. Well, it's the same pressure at 6, but it comes out saturated vapor. So you get H of G at the negative 26 degrees, and that comes in at 234.7. So a lot higher enthalpy. Now you have the enthalpy at 6, the enthalpy at 5, the cooling load. So you calculate the mass flow rate, m dot 2, and the mass flow rate through the second evaporator is 0.0239 kilograms per second. Okay, you know the two mass flow rates. I just need to get that inlet enthalpy and the exit enthalpy to finish the problem. Well, it's not so easy, but let's continue on. From 7, you put it through an expansion valve to get 8. Okay, well 7 to 8 has the same enthalpy. So the enthalpy is 248.9. It's isenthalpic expansion, true? But the pressure is now the right pressure. It's 102 kilopascal. So then I can just mix. I can mix to get 1. Well, the enthalpy at 1 times the mass flow rate 1 plus mass flow rate 2 is equal to the mass flow rate 1 times enthalpy at 8 plus the mass flow rate of 2 enthalpy at 6. That's, you just do an energy balance. I know that the illustration doesn't show you, but it's a little mixing chamber right there. And you do conservation of energy, 2 streams in, 1 stream out. No change of kinetic potential, no heat transfer, no work transfer. You just have m dots times h's. And then you can solve for H1. Okay, so you solve for H1 from this equation, and you come up with, let me finish putting a line in. We find that H1 is 242.3. What pressure is it at? It's at that 102 kilopascal. We then get the entropy, S. It's 0.9814. And we do isentropic compression, 0.9814 to S2. So the pressure and the entropy fix state 2. I look up the enthalpy. It's 290.05. And now I have those two enthalpies. and we calculate the work or the power needed to run the compressor, and it's 2.64 kilowatts. So there are the answers. I have it on another page. If I flip it to it, you'll see that I'd already worked it. So here it is, maybe a little cleaner. I'll pause and see if you have any questions. Yes, sir.
Is that expansion valve at from 7 to 8 there so that it equals the pressure coming from 6?
That's right. If you didn't have it, this pressure would get too low. It'd be the same as 6, and then boom, I don't have a -4 evaporator and a -26 evaporator. I've got two of them at the same. Actually, the flow wouldn't go through here anymore. It would just mess it all up. You're right. It's required. That expansion valve is required to drop the pressure. Yes?
How can you find the temperature at the set to the T2?
Oh, well, you need to really put it on a diagram. So this problem now needs to be put on diagrams, property diagrams. And the two diagrams are the temperature entropy and the pressure enthalpy. So let's go ahead and sketch this out on two property diagrams. So first of all, on the temperature entropy, the one you have more experience with, you look and you say, how many unique pressures do I have for this problem? And let me sketch on how many isobars, lines of constant pressure. So 11 is a unique pressure, 252.6, and the 101.6. So there's really a low pressure of 101.6 kPa, another pressure of 253 kPa, of 912 kPa. Get those pressures, lines of constant pressure down. Then try and get your saturated liquids or saturated vapor states that you know are on that diagram. Wasn't state 3 saturated liquid? So where is state 3 on this diagram? State 3 is right there. Okay. I'm going to probably have trouble with the slope of that line. I'm going to probably have to slope it more like this and probably run into the problem there. Okay. Now, from 3, I go isenthalpic process. And it's going to kick over. Well, no, let me get the other ones down. Where is another state that I'm confident of? State 7 and state 6. State 7 was saturated vapor. So let's put state 7 out there. Right there? Is that where 7 is? Intermediate pressure, saturated vapor? How about state 6? Saturated vapor at the lowest pressure. So we know 6 and 7. I think about it for a minute. Do I know any others that I have any confidence in? No, not really. Now I need to just start working. Let's go to 4. It's at that intermediate, here's state 4. It's at that intermediate pressure. And what is the quality? About 30%. So it's like right here. 4. Dashed line going from 3 to 4 through that expansion valve. Maybe I'll put 4 right there, get it out of the way, the number. Fluid goes along the first evaporator from 4 to 7. True? Okay. Now, let's continue on. Let's go to 5. There's 5. Okay. Then some of the fluid from 5 to 6 goes through that second evaporator. Okay. Now from 7 to 8, it's a little challenging. But where is state 8? Is state 8 on the lowest red line, the lowest pressure line? So I've got to do that. I've got to get down there somehow. Now state 8 could be down in this vicinity, or it could over in this vicinity. I have to figure that out. The data table right here, the state 8, can you tell where it's at? Trust the temperature, enthalpy, and entropy. Where is state 8 going to be? It's in the superheated vapor region. So that's not easy to determine, but that's what it is, okay? So let's put state 8 right there and the dashed line out. How did you tell that state 8 was superheated vapor?
Is it a lower temperature or higher temperature?
Higher temperature than 6? Absolutely. So it's negative 26 for the temperature at 6, but it's negative 9, so it's a higher temperature. Also, look at the S value, S, entropy. S at 6 versus higher entropy at 8. Now, 6 and 8 mix, and they create 1. Where's 1? 1 could be, this is a great clicker question. You want a clicker question? Okay. State 1 is somewhere in this vicinity, answer A. Somewhere in this vicinity, answer B. Or somewhere in this vicinity, answer C. Or answer D, none. I'm looking for the location on this temperature entropy diagram for state 1. Where is state 1? Somewhere in location A, somewhere in location B, somewhere in location C, or none of those. D. D is none of those. All right, everybody's in. Well, the pressure at 1 is a clue that puts you on the line. Isn't the pressure at 1 the same as the pressure at 8, the same as the pressure at 6? So it has to be on that red line somewhere, okay? And so D is not the answer. It has to be on the red line somewhere. Now, if I mix two streams, usually the enthalpy is between the two. Usually the temperature would be between the two. So if I brought in one stream of negative 9 and another stream of negative 26, right, the enthalpy at state 1 would typically between the two. The temperature is an indication of enthalpy.
That's negative 16?
Yeah, that's a negative 16.
Can I change my answer?
Ah, sorry, I didn't mean to have a red mark close to that negative sign. But also take a look at the enthalpies, right? So the enthalpy is between the two, between them two. So, okay, so the answer is B. Pardon?
Well, he says 100%, but X was 100%.
Right here for the quality at 1. Well, the problem with the quality at 1 is if you try to evaluate it in the software, it basically says, it's a quirk of the software. If you try to say, what is the quality of a superheated state, it'll come back with 1 instead of not defined or blow up on you. So, sorry, that's a distractor. Sorry. But I tried to put a loop, somewhere in between instead of being precisely at 6. Okay, so there you go. All right, so we have 6 and 8. Now, there's state 1. Now you put it through the compressor. It's got to come all the way up to this high state 2, don't it? Now it's way at superheated vapor. What's the temperature at 2? A whopping 55 degrees C. Then it's cooled down to the 36, from 55 to 36, and then it condenses to become saturated liquid. So there you go. There's all the states on the TS diagram. Let's do a pressure enthalpy diagram, pH diagram. Could I do the same thing? Could I say, look, I need this pressure, this pressure, this pressure. I need the lowest pressure, which is 102. I need intermediate pressure, 253. I need the high pressure, 912 kilopascal, right? These are lines of constant pressure on a pressure enthalpy diagram. And then I say, this sequence of states over here is all saturated vapor. These sequence of states over here is saturated liquid. And the point is often not at the very cusp up here, but somewhere shifted to the side. But let's avoid the discussion of the critical point right now. We just know that that's the dome. Okay, so where is state 3? It's the high pressure saturated liquid. Is that state 3? Okay, where is now state 7? 7. And where is state 6? So those are saturated liquid, 2 saturated vapor states. On a pressure enthalpy diagram, when you go through the expansion valve, where is state 4 compared to 3? Right below. But you still use a dashed line because it's irreversible. And then 5, dashed line down, and so it's right below. That makes it a little easier on a pressure enthalpy diagram. Okay, now you come across, you're evaporating in the evaporators from 4 to 7 and 5 to 6. Okay. Now, where is state 8 on the pH diagram? It's right below. Constant enthalpy, isn't it? And then I mix them. State 1 is going to have an enthalpy in between. Mass average weighted enthalpy between H6 and H8. And then I put it through the compressor. It's got to get to state 2 way up here. And it doesn't easily show a line of constant S on a pH diagram, but that's state 2. And the temperature is quite high. And then you condense back, well, cool, and then condense back. So just like these lines, H equal to a constant, S equal to a constant, on the TS you have to kind of guess what the H equal to a constant line looks like, and on a pH you have to guess what a S equal to constant looks like. Well, you can put these on real property diagrams to scale. And maybe I should have done that, huh? Because this is the line of 101.6, this is the line of 252, this is the line of 911. And you can do that, put it to scale for the temperature entropy, as well as the pressure enthalpy, pH. This one's probably worth a little bit of time. Why? Because it's negative 26, negative 4, and 36. So right there is state, what was that, 4? No, 3. State 3, right? And then you come out to state 4. Then you come out to state 5. Then you have state 6 and state 7. True? Okay. When you the line of constant pressure would just extrapolate across, and state 1 is a mixture of 6 and 8. I forgot to get 8 on there. Where is 8? 8, you come straight down, and guess what? There is 8. What is the temperature at 8? Negative 9.2. So that's why I drew that line of negative 9.2 to see that it intersects right there. Okay. Then you mix them and you get state 1. State 1 is at negative 16, and it's hard to see, but it's tucked right in there. State 1. And then 1, you compress isenthalpically. It's going to go up to this high pressure that line of high pressure going straight across. And we know that the temperature ends up at 55.3 degrees. That's why I plotted 55.3. You put no, that's a solid line. It's isentropic compression from 1 to 2. Then you cool from 55 to 36, condense 36 to saturated liquid, and there's your cycle on a pH diagram. Look good? Let me do this. I'm going to save my file right now. All right, what I'd like to do now is talk about selecting refrigerants. It's a very practical consideration that engineers are very heavily involved in. When you select a refrigerant, you think of performance. And yes, different refrigerants will have different coefficients of performance, hence there'll be different cost of power consumption for the cooling provided. Also safety, worker safety, environmental issues, they're all very important. So toxicity is a consideration as well as the impact when it does leak out. Refrigerants do leak out, just like a lot of other fluids do leak out. The synthetic refrigerants were first developed quite a long time ago now, 1930s. They were developed because of the refrigerants that were in use were toxic, and they led to a lot of deaths. And before, when I taught this class, I would walk through a few of those newspaper articles, and they're pretty tragic deaths that people had when they were first putting air conditioning systems in homes and buildings and stuff, and then unfortunately the stuff leaked out. And the way the people died is sometimes a little gruesome. They felt like, I forgot the type of chlorine gas that was used. The people in their apartment or in their house would start to feel like high, some sort of a static state, and then they would feel like they needed to take off all their clothes because they were burning up, they were hot, and so they would find them naked and dead. That's how they found the victims. And they would find lots of them. And so then there was a lot of outrage. Man, keep this stuff out of these buildings, apartment complexes, and other things. But so it was very welcome to get synthetic refrigerants that were not toxic, as well as not as flammable, because sometimes they have industrial place, it'd leak out, there'd be a spark, an explosion, a lot of loss of life. So now we almost forget about that. We forget about the safety and the performance. These refrigerants were great. The synthetic refrigerants were great for performance, low toxicity, low flammability. I mean, you can get freezer burn because of those refrigerants, and you can get it sprayed in your eyes, and it can burn your eyes, and it can mess up your eyes. So it's still dangerous stuff, especially because of the temperature, but it's not as lethal as it used to be. But they're very highly stable structures, especially R12 was very, very popular, but it was a chlorofluorocarbons. And these synthetic refrigerants were heavily in use, but around 80s or 70s they started to see the environmental impacts. In 1987, which is now a long time ago, there was an international agreement that banned the production of certain chlorine, that's the bad actor, containing refrigerants. So the new class of chlorine-free refrigerants was developed. One of them, 134A, and it's very popular. If you own a vehicle today, it's probably 134A in your car. That's what you have. And in your residential, probably half of you still have R22 in your home units, but it's being phased out. If you get a new home unit, you can't get it anymore as of the 1st of this year. It's now 410A as the popular refrigerant. All right, so if you take a look at the illustration of R22 and the R134A molecule, can you kind of see which one of these molecules is the chlorine? Because it's missing in the other one. Can you see which one is the hydrogen or the carbon? Here's a carbon. Carbon and a hydrogen. Here is carbon-carbon with two hydrogens. These would probably be the hydrogens. The carbon, the carbon, the carbon, the hydrogen, and the two Fs. I forgot. What is the F? Yeah, the fluorine. Okay. So it's the chlorine that was the bad actor. So taking a look back in 2004, you had the Montreal Protocol, and it banned hydrochlorofluorocarbons, and it set baseline caps and production. And 2010 was a big January 2010. The Montreal Protocol requires the U.S. to reduce its consumption of by blah, blah, blah. As a result, they're not produce any new air conditioner and heat pumps that contain R22. You can't get it. It's gone. You can't buy a new R22 unit. What you're just mentioning is there's still a lot of R22 out there. They can take R22 out of the existing systems, recycle it, and sell it, and it's very expensive. Why? Because it eventually does leak out of systems. And so people are always still buying new R22, typically recycled, and then putting it into a system. Unfortunately, it leaks. They got to buy more and put it in. Okay. January 1st of 2015. What year is it this year? 2015. What month? July, right? So just a few months ago. But this was decided years ago that they required to reduce its consumption of the hydrochlorofluorocarbons by 90% below the baseline established whenever the baseline was. And then January 1st of 2020, refrigerants that have been recovered and recycled, reclaimed, will be allowed beyond 2020 to service existing systems, but chemical manufacturers no longer able to produce R22 to service existing air conditioners, heat pumps. Now, I don't know what's happening in other countries, let's say below the border. I don't know what's happening in Mexico, if you could still get 12. Anybody know if they can get 12 in Mexico? I don't know. I don't know if you can buy 22 in Mexico, but usually if you get a big entity like the United States and the market in the United States, and they basically phase it out, it has a big ripple effect throughout. So even if some people didn't agree to the protocols, it's probably easier and cheaper for them to just purchase what's readily available, and because of the dominance of the market here. So you have the ozone depletion potential. That's really why getting the chlorine out is a big deal. What happened when you release those molecules, they float up way high into the atmosphere, and then they interact with the sunlight, and then with the chlorine busted out of the refrigerant, it then gobbles up some ozone, O3, which is healthy and good up there. At the ground level, ozone's not good for your lungs, your children's lungs, or asthma. But high in the atmosphere, ozone's great because it gobbles up the UV light. And when you get holes, missing ozone, holes in the ozone layer, UV light comes down, people worry about skin cancer, etc. Not as healthy. You don't want to be bathed with that high energy light. But then they start also doing global warming potential. Well, primarily they benchmark it to CO2. Carbon dioxide is a big emitter leading to global warming potential. But you can also say, what is the global warming potential of a refrigerant relative to CO2? And some of them are 3,000, 6,000, 12,000 times worse, pound for pound, so to speak. So what you want to do is you want to get a refrigerant that has a low ozone depleting potential, good, this is good, and a low global warming potential, which is good. So they've knocked out a lot, like refrigerant 12, gone primarily because of ozone depletion potential. If you look at it, it's not very good for the global warming, but that wasn't as big a deal when they knocked it out. And then R22, well, it's not so bad for the either one of them, but it's still being knocked out because it's so much you can do better. And then some of these would really just not be acceptable. You would want to minimize them. And I forget which one of these refrigerants is CO2. Is that R600? Is it R600 CO2? And so there's now a resurgence of using CO2 as a refrigerant. Carbon dioxide. Because if it leaks, well, it's a 1 on the global warming potential, which is pretty low compared to other refrigerants. And it has no ozone depleting potential. So it's just that CO2, you really have to pressurize it. You really have to have a high pressure system. Energy efficiency ratio, EER. You can look this up. It's how they benchmark and compare room air conditioners or window air conditioners. So what is the EER? Well, typically it ranges a rating between 8 and 10 or something like that. The greater the number, the better, because the EER is a ratio of the cooling capacity. So it's like BTUs per hour of cooling divided by the input power electricity in watts. So how much cooling do I get versus W dot electric consumption? That's the EER. Well, because a lot of other things, they like to have the number easy to identify, easy to look at, so something around 1 or 10 is a nice number. So they put this in units of BTU per hour, and that in units of watt, which is got that funny ratio of units to it. Okay. And what's 1 BTU per hour? Well, it's 0.293 watts. Or the reciprocal, 1 watt is 3.412 BTUs per hour. Now, the energy efficiency ratio for these room air conditioners calculated, as you might suspect, on standard outside conditions. The outside condition is, 35 degrees outside. And inside condition, you want to keep it 27 degrees C and 50% relative humidity. So that has to work in that environment. That's the condition, the benchmark. If you have it warmer and more humid, then you have a different efficiency because you'll be condensing more vapor out of the room, wringing more moisture out. And if you have a higher temperature on the outside than 35, well, it's going to degrade the performance. It's harder to pump the temperature, the heat up the temperature scale. You ever seen these little stickers on the side of equipment? Sure. So the energy guide, this is a label put out and recommended by the U.S. government. Give it some authority there. Federal law prohibits removal of this label before consumer purchase. That's good. After you buy it, you can remove the label. Nobody does. But people aren't supposed to remove the label. And you're supposed to be able to, when you go in and make a purchasing decision, be able to find that label and look at it and evaluate it as a consumer. That's to help consumers make better choices. So it's for a window air conditioner. In this area, they describe with reverse cycle with louvered sides. Some manufacturer, model number, and its rating capacity. And so it's 11,600 BTUs. That's a BTU per hour rate of cooling. Okay. They have here an estimated cost, and you like this little scale to be as far over or as far down. Well, since it's cost, you want it as far low compared to similar models. True? See how they word that? Compared to similar models. This one looks like it's going to cost a little bit more per year to run than the other ones. And then here is the EER, the energy efficiency ratio, 9.5. That's pretty good EER. Your costs will depend on your utility rates, of course, and similar models, blah, blah, blah. And the average cost of electricity in 2007, they say, hey, it's around 10.65 cents per kilowatt hour. It's lower in San Antonio, higher in a lot of other places in Texas, etc. Anybody ever looked at these labels? Yeah. Yeah, you should. So in January, starting in January of 2006, which is a while ago, all residential air conditioners sold in the United States had to have a SEER of at least 13. Well, what's a SEER? We just learned what an EER is. You just put a seasonal in front of the energy efficiency ratio, meaning that they let the season vary. They have a standard season. It's like miles per gallon. They have a pattern for the car use. And they put that pattern of car use for that automobile. And so it has to accelerate, it has to coast, it has to push hard uphill at high speed and then go at low speed. They have a whole pattern for how they benchmark and report one number for mile per hour. They don't just put it on an oval and say do 55 miles per hour continuously. They don't do that. It's a pattern. Same thing here. It's a seasonal energy efficiency ratio. So it works well throughout the season on some relatively cool days as well as some hot days. All right. Well, a SEER of 13. Before that, I remember, wow, we got a high efficiency unit, a SEER of 10. Now you can't even buy one. All right. The Energy Star qualified central air conditioning systems must have 14. Anybody ever, the Energy Star? The EPA has done a pretty good job of branding that and then helping. And so people, when they look at new homes or new equipment, is that Energy Star rated? Is it Energy Star qualified equipment? And, it is. Good. I'll buy that one. That's my preference. Home builders use that as well. Okay, after 2005, it's a minimum SEER 13. The window units were still around 10. Here, January 1st, 2015, split system central air conditioners installed in the southeastern region of the United States must have now a minimum of 14 SEER. Well, where is southeastern region of the United States? Yes, Texas is in the southeastern region. It goes from Alabama, Arkansas, Delaware, Georgia, Florida, Hawaii, Kentucky, Louisiana, Maryland, Mississippi, North Carolina, Oklahoma. What do you think is the common denominator in these states? We have some significant summers. Is Minnesota in that list? North Dakota in that list? Montana in that list? Vermont in that list? New Hampshire in that list? They don't have need for high efficiency air conditioners. So, but where you're going to use a lot of air conditioning, you have to step it up. That's what they're saying. You can still buy a 13 up north, but down here you have to have, starting this year, 14 minimum SEER. Split systems installed in all other states must continue to have a minimum of 13, which is the current government requirement. How many people have seen somebody purchase a new unit since January this year? No? Did they have to get the new one? 14 SEER? Don't know. They could have gone with a larger 16 SEER, 18 SEER. You just pay more. Pay more. Pardon? It's around 21-ish. Last year, the electric bill needed to run the air conditioning system was $3,000. They had a SEER of a 13. The system needs to be replaced. Salesman would like them to buy an 18 SEER system. If they do and they install it, what will the electric bill be for next year? You have enough information. I want you to compute the answer. I will give you a little more time than 30 seconds. I think you did well. Let's take a look. Look at, if you buy a SEER 18 and you're going to end up paying more money per year, that's bad news on your electric bill. You go with a higher SEER. What was a SEER rated as? It was cooling divided by the power. And so if you multiply by the time, let's say for the summer, then this is how much electricity you have to buy to keep to provide the cooling in the home. You assume that one summer is about the same, you're going to use it about the same, and so the ratio of the SEERs, it gives you the reduction in the cost. So the W dot times the time of the year is how much you're going to buy if you get the 18 SEER. That's going to be how much you purchased electricity with the 13 SEER, and then it's going to be the SEER of the 18 divided by the SEER of the 13, because you have the same cooling requirement per the year. There you go. That makes sense? You can do a analysis of a cascade refrigeration system. So you have a cycle A and a cycle B. Often they use this if they need to really take heat at a low temperature and dump it to a high temperature. Maybe it's easier to do it in 2 steps instead of 1 step. Here's a problem. Here's the solution to the problem. Same pattern. Basically, here we have different refrigerants, the high side and the low side. So the low side, the high side. You have what helps you fix the state, what do you know, the state numbers, pressures, temperatures. The key is the enthalpy. Sometimes you need the entropy because isentropic flow through the compressor. And look at qualities every now and then to help you. And then you can look at things like the mass transfer rates, the power, coefficient of performance, and even a rate of exergy destruction. You should be able to still do exergy calculations, true? If you wanted to do an exergy destruction calculation, probably do an entropy generation and multiply by the dead state temperature. All right. So you don't know what's under that blue box, do you? But this is now an ammonia water absorption refrigeration system. How does this work? Well, what components are you familiar with that you already know and understand? It has a condenser. You familiar with condensers, how they work, what they do? It has an evaporator. You familiar with how they work, what they do? And I'm going to tell you that water is not the refrigerant flowing through here. It's ammonia, NH3. Ammonia is doing the work of refrigeration in the evaporator, and it's the fluid rejecting the heat in the condenser. You understand the expansion valve, true? But what's under the box? What makes this system work? If you had to guess, just knowing what you know already, you would easily say it's the compressor. Well, what does the compressor do? Ingest low pressure, saturated vapor. Right here, saturated vapor, right? It takes low pressure. And what does it put out right here? High pressure, superheated, or saturated vapor, but it's superheated. I need to condense it. That's why we have the condenser. Okay? Is there any way to do it cheaper? Because what drives the electric bill to run your refrigeration system? The compressor. The compressor is what costs. Is there any way to take in this black box, this blue box, some saturated vapor, low pressure, and output higher pressure, superheated vapor? And if you're far away from a good power source, that becomes very important. If you're trying to live off the grid, or if you have a remote house way out in the boonies someplace and you don't have power lines to it, where you don't have 120 or 240 volts, or maybe you're driving in a vehicle and you want air conditioning, or you want refrigeration and refrigerator, you want it to work all the time, yet you're only running down the road, or you have it parked somewhere, power is a big concern. So you don't have easy access to affordable or cheap electricity. How do you do it? That becomes more practical. Maybe you want to put this in a third world country where they have very spotty electric service. Very important. So what you want to do is you want to really minimize. How can you do it? Well, some engineers thought of it, and it's really clever. It is really, really clever. So let's take a look at uncovering this box. And this is basically the main components of it. So what do we have right here coming in? It's a low pressure NH3. I forgot to emphasize, is that low pressure saturated vapor ammonia hot or cold? It's cold. It's relatively cool. Well, guess what cool ammonia vapor likes to do in the presence of water? Absorb. That's why you took the chemistry class that you took. I didn't learn anything in my chemistry class either. And I took 2 of them. But that's the type of thing you're supposed to learn. But ammonia likes to become absorbed in water, liquid water. So then the liquid water's cheap to boost the pressure. That's the key. That's the secret. It's really cheap to run a pump to boost the pressure. So you boost the pressure cheaply, but now I got to get that ammonia out. Well, guess what? It doesn't like to stay in warm water. It likes to come out of warm water, so you heat the water up. This seems really funny. Why? Okay, I'm really heating and cooling, but this is what you do, is you have a low-grade thermal source to heat up water to drive off the ammonia. Once the ammonia is driven off, that's called the generator. It needs to be cooled down, but it's at high pressure. You put it into the condenser. Now you have a weak solution of water. What do you mean by weak? Well, over here you had a strong solution of water. It's how much ammonia was in it, how much ammonia is absorbed. So if there's a lot of ammonia absorbed in the liquid water, it's a strong solution. But once the ammonia is liberated in the generator, it's a weak solution. And all I have to do is drop the pressure to get it back down to the absorber. You just put it through a, what do you call this? Expansion valve, just to lower the pressure. Restriction. So now I have warm water coming in, cool ammonia, but you know what? That absorber, I need to cool it. To keep it cool so that it really likes to absorb. So I'm cooling the water to help absorb the ammonia. I'm heating the water to drive off the ammonia, and the rest of the components you already understand. And that's basically it. Now I know that there's a lot of enhancement to the cycle, but that's the water ammonia absorption refrigeration. Does water provide any of the refrigeration in the evaporator? Nope, only ammonia, only ammonia. What's the water do? Reduces the power consumption to boost the pressure. Now, there's additional pieces of equipment like a rectifier. You don't want even a little bit of water going through there. You want just ammonia. So you have a little rectifier, really clean it up, okay? Also, this solution is going to be heated in a minute. This solution is going to be cooled in a minute. Why don't you put an intermediate heat exchanger in there so that it helps reduce the load in the generator and reduce the load in the absorber? Great idea. And so there's all these little enhancements that go into the system. But at that, you have been exposed to absorption refrigeration. Okay? Now I'm going to stop, and what we'll do is we'll hand back your design projects.